Okay. So my goal with this sort of lecture series is going to be like to teach the entirety of electronics 2, or my bad, electronics 1. I just given a lecture like the past semester in electronics 2, so that's why that's at the tip of my tongue right now. But yeah, this is electronics 1. I will be teaching the entirety of the course. Um, the thing is, it's like in an 80-minute lecture with your professor is going to see a lot of stuff that's basically filler words and a lot of stuff like that. A lot of the math, the derivations that you see are not really that important in understanding the concepts. So my goal with these lectures is to remove the unnecessary stuff and talk about pure content that will help you to develop an intuition about the course. Going into electronics 1, you will be presented with semiconductor technology and semiconductor physics. However, you need to keep in mind that you're going to have a class in the future entirely based on semiconductors, and semiconductors and the semiconductor physics side of things are not the bulk and are not the main part of electronics 1. The goal behind that is to develop an intuition on and to understand how these semiconductor devices work and how you can, do special and interesting stuff with them. So you will see a lot of math regarding that, and as far as my knowledge goes, you are not expected to be able to derive or come up with any or prove anything regarding semiconductor equations. You just have to understand how these devices work. So with that being said, a lot of the unnecessary derivations I will skip upon. I will go over the intuition, show you how what each variables in the equations actually mean, so then you can right away have the concept in mind through my explanation and can go straight to the equations if you need to apply them. So far in circuit theory 1, circuit theory 2, what we've seen is resistors, capacitors, inductors, maybe even transformers. However, in this class, we're going to start using non-linear elements, okay? What do I mean by this? Devices that have different IV characteristics, okay? When I say IV characteristics, I just mean current voltage. So let's say you got this device here. It's called a diode, a PN junction. P for the positive side, N for the negative side. Okay, let's say I apply a voltage across this diode, and as we all know, current's going to flow from high potential to low potential. So you got a current flow flowing through this diode. What's special about this PN junction is because of its semiconductor properties, it's only going to let current flow in one direction, okay? So if I were to invert this voltage right here, this current, right, it wouldn't flow, right? There would be no current flow in this direction because of the semiconductor properties of this diode. And one of the things you need to understand is that diodes and any transistors, MOSFETs, BJTs that you'll see in the future, they are based on silicon technology. However, silicon by itself is not interesting. So the way to really make it work in a full-on circuit is to add phosphorus and boron in it as impurities, and that's how we get interesting effects on those devices. Okay. So look at this graph right here. This is the current, this is the voltage. So this current right here, I want you to picture as this current going through the diode, okay? And then this voltage right here is the voltage across the diode. And as you see, as the voltage increases, before I mention anything further, this blue graph right here is for an ideal diode, and the red graph is for a real diode. So I'll talk about the ideal diode first. So let's say I increase this voltage, okay? This voltage, I keep on increasing it. So you will see that in the forward region, when the voltage is positive, greater than 0, the current is going to go up, okay? There's current flow through the diode. And as the voltage is increasing, so the current, okay? And one thing you got to see here is that VZK. That VZK is the breakdown voltage. It's the negative voltage at which the diode starts to break down and it stops conducting current, and it starts to actually conduct current in the opposite direction. So what I want you to see here is as the voltage is positive, the current is positive, so it flows in this direction. But at some point, VZK in the negative side, right? So if I put VZK right here, going in this direction, it will actually allow a current to flow in this direction. That does not mean the diode is damaged or anything like that. It just means that the alignment of the charges inside of that device is cannot sustain that VZK in the negative end. That voltage is so negative that it has to let current pass. Okay, at some point it's gonna break down. That's what we call the breakdown voltage of that diode. At some point in the negative voltages, that diode will break down and will start conducting current in the opposite region. Generally, we do not want that to happen. We want to operate the diode in the forward region so that we can direct the flow of current in our circuit, because as I've said, the diode is a device that's going to allow you to move current in the direction that you want. So you can kind of place diodes very smartly in a circuit to be able to direct current in ways that you want, and that can benefit your circuit further. So now let's look at this red curve right here. This red curve, you kind of see that we got something exponential going on here. So when the voltage is positive in the forward region, so the graph is going to exponentially increase a little bit, and then it's kind of going to, go totally vertical at some point, right? It's like approaching an asymptote real quick. Here, this red line, if I zoom a little bit more, you will see there's a red line going on here. This is a very small current, right? Ideally, it's not going to be exactly zero. It's the real world. So it's going to be like to the order of 10 to the negative 15 milliampere, very small. So approximately, and it can be considered basically zero. And again, we go to the point minus VZK, which I said as the breakdown voltage. So at that point, what's going to happen is that as the voltage increases here in the forward region, you're going to see that the diode is going to conduct current positively. But here, after, if I go further away, more negative from that breakdown voltage, right, the current is going to start to flow in the other direction, which is basically what we talked about. So if I have some voltage, right, say something bigger, much bigger than VZK in the negative end. So I'm talking about a voltage maybe here. So that current is going to start to flow here in the negative, in the opposite direction. So that's why we call the breakdown the breakdown voltage at which the diode starts conducting current in the opposite direction. So let's move on here. So this diode here, okay, this little triangle, I want you to see this triangle and imagine that the triangle's tip is kind of pointing in the direction of the current. So now if I were to expand this thing that's in the middle, this triangle further, we get something like that. This rectangle separated. So we got p-type and then n-type, right? This separation does not have to be physical. It's just like a p-type and an n-type. What do I mean by a p-type? A p-type basically means positive charges and n-type means negative charges. So let's say I have a p-type. It does not mean that this section of the diode is composed only of positive charges. As you can see, if I zoom a little bit closer, you also got negative charges in here. But the thing that you got to keep in mind is that there's more of the positive in the p-type, hence the name p-type. And the same thing applies for the n-type. There's more negative charges, so that's why it's called an n-type, okay? However, you still got like small, opposite charges at the minimum on both the p-type and the n-type, okay? It's just at the very minimum level. It's about what the majority actually is. So now what is a p-type? A p-type is a positive charge, as I mentioned. An n-type, we all know those, electrons, negative charges. So now let's say I have an electron here, and I put it in an electric field here. So this is plus. Actually, I'll make electron so I have more room. So I'll call this one minus here, and then this one plus. And due to physics, we know that this electron is going to be attracted to the plus side, right? And it's going to be pushed away from this negative side because of repulsion. So after some time has passed, this electron will move and will take place, will move right here. Hence, it's going to leave a blank spot right here. This blank spot is going to have nothing in it. So we consider that to be a positive charge. Okay? So positive charge are not protons or anything like that. It's due to moving electrons. You had electrons in one spot, it moved to the other side, so it left a hole. That hole is called a positive charge. I hope that's very clear because it's a very important concept. I'll say that one more time. If you have an electron that moved somewhere else, it left away a blank space. That blank space, because it's got nothing in it and an electron moved away from it, is considered to be a positive charge. Okay, so this is what's going on in the p-type right here. Okay, it's kind of like the electron moving. Electrons moving around in the circuit is giving a sense that the holes are moving around, but the holes are not really moving around themselves. It's just that the electron are leaving blank spots after blank spots after blank spots, that it kind of gives a sense that the holes are actually moving, if that makes sense. If you kind of imagine it a little bit, it will make a lot of sense. So one thing that's very important in physics is diffusion. And generally speaking, diffusion occurs when you're moving from higher concentrations to lower concentrations. Okay, so from more to less, as I wrote it right here. So here we know that we have more holes, more positive charges. Here we have more electrons, more negative charges. And we have less here electrons and more holes. So naturally, these holes are going to want it to diffuse to the n-type, okay? Because there's not much holes right here. So it's going to want to go here because you got a lot. Same thing. You got a lot of negative charges here, electrons, and then you got small amount here. So it's going to want to diffuse to the other side. That's what's going to happen. The electrons are going to want to diffuse to the other side. So diffusion is going to occur. And what's going to happen is that when you have diffusion, right, you have moving charges. And moving charges over time, if you think about it for a bit, it just means it indicates a current flow, all right? Diffusion means flow of charges, high concentration to low concentration. So it implies a current flow. But if you look at the circuit right here, you got an open circuit here, you got an open circuit here, correct? What does that mean? No current, no current. So if diffusion is occurring, that means at some point a diffusion has to stop because physically speaking, you cannot have any current flowing in an open circuit, right? So it's physically impossible. So that's why I wrote right here that the diffusion is going to have to stop. And how does the diffusion stop? Is like if you look over here, this is your diode, and then this is your kind of the rectangle that I was talking about earlier. After the diffusion, some of the p-type went to the n-type and got stacked right here, and some of the n-type went to the p-type and got stacked right here. Okay, so that's what happened after the diffusion has stopped. And this region right here with the plus and the minus, right? We call that the depletion region, right? The depletion region. There's a small like little rectangular width right here after the diffusion where you have plus and you have minus. So if you look over here, the current still zero, current still zero. But this region, if you pay attention very closely, you got positive charges, you got negative charges. That means you have an electric field going on over here. And when we're talking about circuit elements, right, we're talking about, we rarely talk about electric fields. However, there's a scalar quantity that represents an electric field in the languages of circuits, right? We call that a potential, a voltage. So if you have an electric field going on here, that means you got a built-in voltage. That built-in potential here is denoted by V0, and that V0 will be derived in your lecture. That derivation, you're not responsible to understand all of it. You just have to understand what each uh, element inside of that equation, what they represent, and how you can apply them. That's all that matters to you. Okay, so that's your V0. Okay, next thing here, if I were to apply an electric field outside, right, an electric field in this direction right here, okay, to this circuit, what do I mean by an electric field? I'm just saying if I were to connect the voltage source right here, plus minus, I were to connect it right here. So you got an electric field flowing in this direction. What's going to happen? What's going to happen is that these n-type right now, if they're connected right here, they're going to be attracted to this positive thing, right? Opposites attract. Same thing. These p-types, these holes are going to be attracted to the negative end, okay? They're going to be attracted to the negative end. So it's kind of going to split that a little bit further, okay? And then you're gonna have your depletion region right in the middle. So it's just gonna make everything a little bit more obvious. So the electrons, okay, are gonna be attracted to the positive, and the holes are gonna be attracted to the negative. So then, one thing I want to make sure you understand here is the diffusion and the electric field on the outside are two different things, okay? So the diffusion, the movement due to diffusion, the current from that, because it's a moving flow of charges, we're going to denote that as the drift current, the diffusion current, sorry, okay? The diffusion, okay, from positive to negative is going to be called the diffusion current. And after applying that electric field on the outside right here, this is going to be called the drift current, okay? The drift current through the circuit. I don't know why I did this. The current does not necessarily have to flow in this direction. Here. Okay. Now, the electric field helps minorities while ditching majorities and drifting movement due to the electric field. So, what do I mean by this? Remember, as we said before earlier, right? You have diffusion occurring. So you have more on one side going to the less and less going to the more. Okay. So let's say you had a couple of negatives here, right? So these one sec, I'm just gonna blanking out a little bit here. Right. We're back. So say you had some negative charges in here, and then you have some positive charges in here, right? A lot of that positive charges here, we're going to diffuse over here, and a lot of the negative charges here are going to diffuse over here. But if you're connecting here to a voltage source plus minus right here, this negative, say you have some negatives here, is going to push these negatives into that depletion region, okay, further. And then this positive with the minority positive here is going to push these positives into the depletion region. So that's what I meant by here, okay? My bad. So the electric field is basically going to allow the minorities to move better while ditching the majorities. The majorities are kind of going to stay still. And drifting, okay, basically means movement due to the electric field. So as I said before, you're going to have two types of current. You're going to have a current due to diffusion, and then you have a second current due to the electric field that's applied. And now let's talk about the built-in potential right here. The built-in potential that you'll derive in class is this equation, Vt ln and I squared over Na and D. Vt means the thermal voltage, which is Kt over Q. K is the Boltzmann constant, this is the temperature, and this is the electron charge. However, in that course, Electronics 1 and Electronics 2 even, whenever you have to use Vt, you can straight away use the value 26 millivolts. That's correct. And I, what does that mean? It's the intrinsic carrier concentration. So if you're given a problem, you're going to be given all these values to be around to be able to play with. It's basically just a little bit of algebra, isolating for what you need. You just have to understand what each term mean. So and I is the intrinsic carrier concentration, and A is the acceptor doping concentration, accept electrons, creating holes. It's in the p-type material. And D is the donor doping concentration. It donates electrons, and it's in the n-type material. Okay. And D is the, I don't know why I wrote this a second time. There we go. K is the Boltzmann constant. T is the temperature in Kelvin, and then Q is the electron charge. Okay. So now if I scroll down a little bit, so an ideal diode that you'll see in the future is represented by this short circuit or open circuit. So we said that the diode, if we put a positive voltage across it, right, is going to conduct current in this direction. So it basically, if it's an ideal current diode, it's going to act as a short circuit. So current is going to flow. If I place a voltage like this, okay, on this diode, that means it's not going to let current flow. It's not going to allow it. So it's going to be represented by an open circuit. So that's for an ideal diode. However, a lot of times we don't deal with ideal diodes. We deal with real diodes. And we said that the real diodes is associated with some sort of voltage, and of course, any element in a circuit, even a wire, has a resistance, right? So the diode would also have a small amount of resistance. So this diode here, you have a diode connected to a voltage source called VDO, and then this is going to be RD, the resistance of the diode. Okay, and of course, if this diode is on, it's going to be like this. And if it's off, it's going to be an open circuit, right? Basically the same thing. So I hope I was able to, kind of give you a lot of the intuition without going through a lot of math and getting lost in the math. Of course, I got lost a little bit here. I had to figure out what's going on, but I cleared things up. It was okay. So with that being said, watch out for future videos. Um, I'm really excited to be going forward with this idea of uploading my own lectures here. It's been very successful in the past, and I've gotten a lot of requests for it. So this is what I'm doing, and I hope you enjoyed this kind of content. And if you want to see more sort of electrical engineering or physics side of content from an unconventional small YouTuber, please hit the subscribe button and like, please. Thank you.